I feel like sometimes when I get stuck, I like to solve an easier problem and then go back just because it helps my brain work better. So we have a circle passing through A and G, where G is some other point here. And then the bisector of angle BAC meets that other circle at K. So let me move things around so we can see the intersection point. There we go. So that will be point K. I'm sorry, that'll be point P. So maybe it's also worth drawing this point right here. So that's the midpoint of arc BC. The point E is on the circle, so AE is parallel to BC. So that's interesting. So this right here is point E. And yeah, I'm gonna have to rename the other point E. I'll try to make this as flat as I can. PK meets the perpendicular bisector BC at F. Oh, I didn't draw point K yet. So K is going to be the center of the circle. And we want to show that angle EGF is 90 degrees. Let's make this look a little better. So yeah, I'd like, okay, G has to be on this arc. We make it like a flatter triangle, maybe something like this. So there we go. So PK, so this is point F right here. This looks like a good problem. I kind of like this. Oops. So AE is parallel to BC, and then AP is the angle bisector. And then, yeah, this is a good problem. So we can draw the midpoint of BC if we want. We want to show angle EGF is 90. Wait, where does point E? Oh, never mind.
I intersect EK with the circle.
Yes.
Circle with center K.
So we have EH as a diameter. So basically we want to show GF and H are collinear. I don't think E lies on OG. That would be too good to be true, but Okay, so we know it might be, like, sometimes I like labeling this point because like we want to use that AP as an angle bisector. So I let AB meet the circle also.
Well, AH is perpendicular to BC and parallel to OF, which implies GDFP is cyclic.
GDFP. Okay. So how did you get AH? So because AH is perpendicular to AE. Okay.
Yeah.
And then an angle chase gets that's cyclic.
No, actually, I guess we want to prove it.
Oh, we want to prove that it's cyclic.
Yeah, let me think.
Oh yeah, in center X center lemma looks possible. All right, so we want to show that's cyclic. Let's see. Is G is the common point of three? Is G a Miquel point? Yeah, could be. All right, so we have another person joining.
Yeah, I think we can prove that G lies on that. I think we can prove that G, D, F, and B is
GDF and P are cyclic.
yeah, by labeling the section of OM and circumcircle ABC.
So this point right here.
Yeah. No, I mean the other one.
Oh, the other
Like
circle.
the big
Okay. This point up here, or
yeah,
or
and yeah, that point up there.
all right.
And then we label the intersection of JA with circle K.
Okay.
Yeah, and label that point. Then it must be collinear with K and B.
Okay.
Yeah, and then G is the Miquel point of the quadrilateral ADFL.
ADFL.
Yeah,
Yeah. That is I like it. So we have
Yes,
G.
angle change.
So GDFP would be cyclic because GDAJ is cyclic. And yeah, we have GDAJ is cyclic and GALP is cyclic. So I think we probably have enough to solve it, right? I think that probably does it. So
Yeah, FGP equals to FDP equals to HAP.
GDP,
No, FGP
FGP,
equals to FDP, and it equals to HAP.
just equal to HAP. Oh yeah, you're showing how to finish it off. Yeah. So then those three would be collinear, and then that would solve it. All right. So I will write that up. So let D be the midpoint of minor arc BC, and let DJ be diameter the circle ABC. Let JA meet the circle AGP. Hold on. Or I could just say the circle K. Intersect the circle K at point L. Okay, so then, well, yeah, it's obvious A, D, and P are collinear. And then, hold on just 1 second. All right, so, sorry, I had to do something. All right, so Hoy just joined us again. So A, D, and P are collinear, and PL is the diameter. So PL passes through K. So all right. Did we need point H for this proof? Yeah, I guess because you eventually used it to do the angle chase. So so basically G is the Miquel point of quadrilateral ALFD. And that's because ALGP is cyclic. So we have ALGP, and then the other one is AJ DG. Those are both cyclic, so that's why it's the Miquel point. And then once we know that, that means that GDFP is cyclic. So we can draw that circle. And now it's just kind of an angle chase because FDP, so we want to show G, F, and H are collinear, but we could show angle DGF, DFG, DPG, which is APG, which is AHG. So that means that F, H, F, and G are collinear. Well, first we want to use AH as parallel to DJ, but that's obvious. That's kind of by definition. So I'll say let EK meet the circle K at H. I'll just say let EH be a diameter of K. So then that implies, since angle EAH equals 90, then that means AH is perpendicular to BC. And then that's where we use that. So we have AH is parallel to DF, implies GF and H are collinear. And then from there, it's easy to see that angle EGF equals 90. So I'll just say EH is a diameter, and that means angle EGF is 90. All right, I will move on to the next one. Let's see. We have a little over an hour. So this is from 2016. Let me check the chat. Oh yeah, we solved the very first problem. So yeah, we have a triangle ABC and a circle O. This looks like a kind of similar idea where you take the angle bisector. So I'm going to draw the perpendicular bisector BC. And then we get points D and E. So it cuts the circle at D and E. And I'll just draw the center of the circle, call it O. Let G be a point on arc AB, which doesn't contain C. GD and BC intersect at F. Whoops. All right. So I see a lot of people on my channel are from Vietnam. So I want to thank Vietnam for all their support of my channel. Really appreciate it. So H lies on AG such that FH is parallel to AE. All right. Okay, so this is point H. And we want to show the circumcircle of HAB passes through the orthocenter of HAC. That's interesting. So I'm going to turn these just into segments. Okay, so FH is parallel to AE. That's kind of interesting. And okay, so maybe I want to draw the orthocenter of HAC, and then I want to show that it makes a cyclic quadrilateral. I think that might be a good way to go. So here's triangle HAC.
I think it is not necessary to draw the orthocenter.
Oh, really?
Because that is just another way to say that angle HBA is equal to 180 minus HCA.
HBA is 180 minus HCA. Yeah, because the reflection of the orthocenter over the side lies on the circumcircle. That's a good point. So yeah, if we know that HBA is 180 minus HCA, then that proves it. I like that.
Because working with that random orthocenter doesn't look very good.
Yeah, I agree. All right, so I like that idea. So H is on AG. Okay, so we want to calculate the two angles. I don't know if it's worth drawing this point right here. So I'll just do it. So yeah, how do we use the parallel lines? Maybe we could let AB intersect. I mean, it's also the same as showing angle ABH is ABI, right? So it's kind of like we want to show AB bisects. Well, we want to show AB bisects angle BH HBI. So yeah, the reflection of I over AB should lie on AG. I'm sorry, it should lie on HB. I wonder if there's any cyclic quads passing through H. Is HBFT cyclic? No.
Looks like HF is the angle bisector of BHI.
Ah, interesting. So we have one angle bisector. I don't, let's see if we
Can
could,
you label the intersection of HB and the circumcircle?
yeah. Sorry, my computer froze for a second. Is AJ parallel to BC?
Yeah, I was thinking about that, but I wasn't sure.
Let's see.
Nah, I don't think it is.
No, it can't be.
Yeah, so you can just remove it.
But it's interesting that that's an angle bisector.
This looks a lot like an Apollonius circle.
Yeah. So maybe I should draw the perpendicular to FH. And let it intersect BC.
You should also note that GF is the angle bisector of BGC.
Yeah, because, oh yeah, that's obvious because these are the midpoint. So we have a lot of angle bisectors. Like, yeah, so these two angle bisectors, I mean, we don't know yet that HF is the angle bisector, right? But basically, so basically we want to show GKHF is cyclic. And maybe this is where the parallel comes in, because FH is parallel to AE. So angle HFK.
Because of the parallel lines, you get that HK is parallel to AD.
HK is parallel to AB. But the thing is, we don't know yet that, I mean, if we could prove that, that would solve the problem. I mean, because really we know, like we know GK is parallel to GD, but we want to prove that HK is parallel. I'm sorry, we know GK is perpendicular to GD, but we still have to prove that HK is perpendicular to HF, right? Like do we know that HF is an angle bisector?
No, we don't.
Okay. So yeah, maybe we could show that this is cyclic right here somehow. Let's think about it. So, oh, and this passes through E. I should draw that. So basically, the angle that FH makes with FK is the same as the angle that AE makes with BC, which is the same as angle ADE, which is, yeah, so I think it's easy to prove by an angle chase that this is cyclic using the parallel fact. and then we would know, like then we would know all that stuff. We would know that HF is the angle bisector, and we know HK. So yeah, I think an angle chase proves that H lies on the Apollonius circle. And once we know that, feels like we're very close then, right?
Yeah, an angle chase does it. So that is good.
Okay. All right, let me write this up. So we'll say let BC intersect EG.
Why should you write? We haven't done the problem entirely.
Oh, so once you know this is cyclic, oh, are you saying an angle chase proves it's cyclic, or an angle chase, or once we know?
Proves the cyclic.
Yeah. Okay, so we still have to show that. Okay, so yeah, we want to show that angle ABH is ABI. So let's see, ABH, it's 180 minus GAB minus GHB. I wonder if K, so GHB is GKL or GFL. Can we say about point L? I'm not sure if there's really anything special about point L. Yeah, the key is to calculate angle ABH. It's just finding the best way to do that. So angle ABH, we could say it's like ABG plus GBH. Is B the in-center? Yeah, because I wonder if we can somehow find an in-center. Yeah, because HF bisects this. So if AB meets HF at a point, that should be the in-center. So basically, we want to show, if we draw this point, we want to show it's the in-center of HBI. Maybe we could use like the in-center x-center lemma. Let's see if BMIF is cyclic. I have a feeling this might be like the in-center x-center lemma. Ah, it's not. Okay. What if, so yeah, the goal is to show that M is the in-center of HBI. Are M, I, and D collinear? Ah, so I think that might be the key. It looks like M, I, and D are collinear. So is it obvious that, so we want to show AB, HF, and ID concur. And then an angle chase should do it from there.
An angle chase shows that ID is the angle bisector, or BIH.
Oh, really?
Yeah.
Yeah. Oh, yeah. Yeah. So basically, yeah. So once we know that ID and M concur, that would solve the problem.
And they're yes, it is enough to show that those are collinear.
Collinear. Yeah. Do they also pass? I don't think it passed through K, right? No. Or we could define M to be the in-center and try to show A, B, and M are collinear. There's a couple ways to do it. Maybe it would help to draw the circumcircle of the HBI. See if we could use the in-center x-center lemma. Sorry.
Sorry, Michael. If we have HM is the angle bisector of angle BHI and angle BMH is equal to 90 degree plus angle BIH divide 2. Is it enough to prove that M is the center of triangle BHI.
Okay, so yeah, so you want to calculate angle BMH, and if you can do it in terms of BIH, then you can show it's the in-center. Okay.
Yes. And this is easy to calculate angle BMH.
Mm-hmm.
Yes.
And it's angle BMH, it's angle like 180 minus GAM minus GMH, right? Or do you have an idea how to do it, or that's just kind of what you were thinking?
Yes. Angle BMH is equal to angle BAE.
BAE
Is equal to, yeah.
Okay. Yeah, I think that's
But I think we need to prove that IM is the angle bisector first, because the point M can just lie on the the circle passing through BH in the center, and that equality is still right, even though M could be like another point other than the center.
well, so basically we could prove that M lies on the angle bisector BHI, right? So we proved that. So I think Khan's idea worked, or I'm sorry if it was Khan or Geo King or maybe it was someone else that mentioned it, or when, but I think this idea works. So basically we define M to be the intersection of AB with HF, and we can prove HF is the angle bisector. We did that with this Apollonius circle thing. So if we also have like angle BMH in terms of angle BIH, and we can show that a certain equation is true, then that proves that M is the in-center. So I think this should solve it. So here's the ideas. Okay, so yeah, exactly. So yeah, I think this will do it. Okay, so let's see. Let's draw the points I added. So we want to let HC meet the circumcircle of ABC at I. So we're going to draw I and K. And let EA.
Did we use I in the solution?
So we want to show M is the in-center of HBI. Yeah. Sorry. So let EG meet BC at K. And so that means that angle KGF is 90. And then we also have GF. So is F even, yeah, F is mentioned in the question. Lines G, yeah. So GF bisects angle BGC. So that means that KGF is an Apollonius circle. And Apollon, I forgot how to spell this. I think it's like this. Okay, and then we can try to show that GKHF is cyclic. So So actually, I'll start out. Let A, B meet H, F at M. Okay, and so since FH is parallel to AE, basically we want to show, so the angle that FH makes with FK is the same as the angle that AE makes with FK. So I'll write it like this: the angle that FH makes with FK is equal to the angle that AE makes with BC, which is because they're parallel, because FH is parallel to AE, and that is equal to the angle that DE makes with AD, which is equal to angle ADE ADE, which is angle AGE, which is angle KGH. Did I do everything right here? Let's see. Because how is it? Yeah, because H is defined to be on. Okay, so that means that FGKH is cyclic. And that implies that H lies on the Apollonius circle. So basically we have HM bisects angle BHI. Then we could do that calculation. So angle HMA, angle HMB is HMA, which is BAE. HMB is HMA, which is angle BAE. And we want to write that in terms of BIH. So BAE is, I kind of just assumed things would work out here, but that should be 90 plus A over 2. And that's 90 plus 180 minus angle BIC over 2. And that's, if you work that out, we want to find that in terms of angle BIH. So 180 minus BIC is BIH. Actually, we could just say this is 90 plus angle BIH over 2.
And that is enough.
Yeah, exactly. So that means that, actually, let me get rid of this, see if it works. So M is the in center. Oh, well, I'll just leave it like that. So, because I want to have enough room. So M is the in center of triangle BHI. And then once we know that, we have angle ABH is ABI, which is 180 minus ACI. And then that means the circumcircle of HAB passes through the orthocenter of HAC. Let's say since the reflection of the orthocenter over each side lies on the circle. I like that. It fits right here. All right, so we have 40 minutes left. Did I do that right? ABH is 180 minus HAC. Yes. All right. Maybe I'll write 180 minus ACH. So now we can go back to the other problems. So do you want to go to, so I feel like we were closer. That one we already did. We go back to this problem. Be right back.
We can try to show that C has equal power with respect to AMN, AQP, and the circle through R orthogonal to the circle. Then it will show that
Wait,
R.
Michael is not
Oh,
here.
he's away.
But were you saying to prove that C lies on AE?
Yes.
I think I know already how to prove that.
How do you prove it?
What did you say?
All right. I am back. Let's see if we can solve this in the remaining just under 40 minutes. This looks like a good one. RA equals RJ.
Maybe it is good to try to calculate the power of R with respect to the incircle.
Okay, so
Because that power should be RA and RJ squared.
so RA squared equals like RA and RJ because it's orthogonal. Okay, so yeah, so maybe we could try, yeah, calculating the power of R. Can we use the power ratio lemma? Okay, so we know R lies on the polar of H. And H lies on the polar of R. Maybe we could show Ri is perpendicular to FG. Because yeah, that would solve it if we could show that. What if we draw Pn? Does Pn, Qm, and Bd concur?
Yes.
Is that obvious? Let me think.
Well, the proof isn't obvious, but it is similar to,
Pascal's. It's probably Pascal, right?
well, I didn't use Pascal to prove it, but maybe yes, probably.
Probably.
It's quite obvious. You can use Mendeley's theorem or something like Pascal theorem.
I'm sorry, did you say you could use a lemma to prove it?
If you define O is the intersection of QM, and Pn, it's quite obvious that O lies on BD by Mendeley's theorem.
Menelaus. Okay. All right, so I'm just going to leave point. I don't even know if O is helpful, but I'm going to leave it there just in case. Let's see. All right. So that might be useful because RGI is supposed to be like 90 degrees, right? And then, wait, I'm a little confused here. So RG, oh, not RGI. It should be, yeah, shouldn't RGI be 90 degrees if they're orthogonal? So RG is parallel to, we want to show RG is parallel to OM, right? But it almost looks like they intersect, so they don't look, for some reason they don't look parallel.
Yeah,
Yes,
it isn't. It isn't.
They're not parallel. Okay. But isn't RG perpendicular to, oh, because it's AI versus IG. That's why I got confused. Okay.
Yeah, the point G was too close to IA.
This almost looks like IMO number 3 of this year, because it's like we could let R be the circumcenter of A, J, E, and we want to show that R, L, and K are collinear. So we want to show it's like the collinear with 2 of the centers of the circles. It's one way to think about it. So yeah, can we find the power of R with respect to the end circle? Let me try that idea one more time. So T, yeah, those should be collinear. So yeah, actually, we also know that T, O, and M are collinear. So or wait, I don't know if we do know that, but I'm gonna draw it. It almost looks like AMHT is cyclic, although I would be very surprised if that was true. Actually, maybe AJHT. No, that can't be. Let's check the chat. We haven't used the fact that the end circle is tangent to ABCD. Well, I think we've used it a little bit, just not totally, because like I think we needed to use it to show that H exists and that all these lines are concurrent. Yeah. But we don't have any info on R. Yeah, we need to use that L is like the circumcenter of AMN and K is the circumcenter of AQP.
The circumcenters aren't really important. It is more that R is the intersection of the perpendicular bisector of AE.
Yeah. Oh, that's true. Maybe it's worked around the midpoint of AE. So yeah, I like the idea. We want to calculate the power of R with respect to the end circle. If we could show that power is RA, that would solve the problem, right?
Not so sure, but that would be a good promise.
Okay. So is there some line through R? Maybe we could use Casey's theorem. are D, I, and K collinear? If that would be true, then B, I, and L would also have to be collinear. It looks like it. Yeah. Is that obvious? Let me make sure that's actually true. But yeah, it looks true.
Because of the perpendicular bisectors, it's obvious.
Oh, it's obvious. Okay. Well, that's good to know. So yeah, it's not just the diagram. It's actually true. Because draw this. Because yeah, by symmetry, I mean, we have dp equals dq, so dk is the angle bisector of that circle of AQ, of the certain circle of AQP. Yeah, because DI is the perpendicular bisector of PQ, and K, yeah. I like that. I think that has to be useful somehow. It almost looks like DL is perpendicular to BK. I'm not sure if that's true. Or it might just be an angle shade. No, it's not true. Don't think this is cyclic, but it's worth checking. Yeah. So we want to show FG is the polar of R. Can we find another point on that and show it lies on the polar? It's like if we could draw if we drew this point and showed it was on the polar. Maybe we could use projective geometry. So we basically, we want to show H, F, S, G are in harmonic conjugation.
Which points did you say harmonic conjugation?
F, G, S, and H. If we can show those are in harmonic conjugation, I think that solves it. Because we know R lies on the polar of H, and if we could show that also S lies on the polar of H, then I think that would solve it. So yeah, I mean, if we rephrase it another way, really we just want to show like if the end circle meets BD at a point, then we want to show like HU would be tangent to it.
How do we define S?
It's the intersection of FG and BD. And F and G are the intersections of AEG. Or I'm sorry, AJ, the circle AJ E. But yeah, I just don't see where we would project S through. So yeah, I'm not sure how good of an idea that is.
How does RSDB or in harmonic conjugation solve it?
Oh, I was thinking H, S, F, G. But if we know that those are in harmonic conjugation, then that means that S is on the polar of H. And we also know that R is on the polar of H. So,
We already know that BD is the polar of H.
we already know that BD is the polar of H. Okay. Wait a sec. So we want to show that FG is the polar of R, right? Yeah, sorry, I kind of went in circles. So it seems like a very, so RI perpendicular to AH. Let's see. Might be. I don't think so, because RI is perpendicular to FG, but AH isn't parallel to FG. So RI is perpendicular to FG. Yeah, RI is perpendicular to GH. It's an OI. Well, so this circle, we're trying to prove the circle is centered at R, right? And the end circle we know is centered at I. So if everything was true, these two circles, since they have center R and I, it should be perpendicular, RI should be perpendicular to FG, right? And FG passes through H. So that's why I was thinking that. So I'll draw it out. So, okay. Sorry. So I guess another way to do this, I can draw this point right here. Dang it, I'm just gonna delete that. So if we call that S instead, we want to show, so RS squared is RA squared. And yeah, I don't think RA is tangent to the circle, right? No. Basically, we want to show RS squared as the power of R with respect to the end circle. So if we let BD meet the circle at U and let's say V, I'm gonna have to zoom in to do that, but probably even more. There we go. So we want to show RS squared as RU times RV. Which is the same as saying, yeah, I'm really not sure right now, to be honest. It's just, I think it's the same as saying that S, U, V, and this point over here are in harmonic conjugation. That doesn't even look true. Actually, maybe it is true. Whoops. And it almost looks like VP and UN meet on AC. Yeah, no, I agree. Yeah, VP and UN look like they meet on AC. I'm just going to delete U and V though. But yeah, I think we're missing something. So yeah, let me see. I'm trying to use the radical axis theorem. Maybe there's a way to do that. I'm not sure here. I'm going to show RA equals RJ. There's one problem we did on the Discord once where I think we did something similar where we showed like RA is equal to RJ like this. And I think we extended AI and we let it meet the circle again. You know what? So here's the thing. If we draw the circumcircle of ABD, basically the perpendicular bisector, oh, I already did that. The perpendicular bisector. So like, what if I drew the incircle of ABD? Yeah, the thing is this circle is, it's not the incircle of ABD. That's what makes this tricky. So like, if I draw the line perpendicular bisector. And I try to see where it meets this circle. Is there anything special about these points? So W, it's not the midpoint of arc AB. But maybe there's something else special about it. If I drew that, we know VA equals VJ. I'm gonna do it for one more minute and then I'll stop. I feel like this might be a generalization of a problem that I posted on Discord. Like in the case where like ABD is like a triangle and E is like the point of tangent C, that would be kind of interesting. So we could think about that sort of degenerate case. So like what if we take like a triangle in the incircle? Let me check the chat. Equals Miquel points. Yeah. But like, what if we consider like the degenerate case of this? So yeah, I'm wondering what if what if we take the degenerate quadrilateral ZA1DB1 and then we like did this problem. So we have AMN. So then it would be the circumcircles of ZED1 and ZFD1. Oh, yeah, then it would be like very symmetric. Interesting. I'll have to think about it later. Anyways, I think I'm going to stop here. So for everyone watching on YouTube,
I have an idea, but I don't know if I can really do that. But can you just let me present?
Yeah. If it's just a couple minutes, yeah. Tell me what you're thinking.
It's kind of risky, so I'll draw the intersection of BD with the incircle. So you already have point U, so let's call the other one V.
V.
Or
Okay.
something else. We already have V. Let's call it something else.
All right. Call it Z. Whoops. All right.
Okay, so I was trying to prove that GZ over GU is equal to AZ over AU. So because R is the center of the Apollonius circle of the ratio GZ over GU, so somehow if we can prove that ratio, so RA will be equal to RJ.
Okay, so you want to show GZ over GU is AZ over AU? JZ over JU.
Yeah.
Okay, so that would basically mean these. And it looks like GS is actually,
Yeah, the angle bisector, right?
Yeah, that's interesting.
It's not really working out because AU over AZ is kind of a little hard to tackle it.
To figure out. It's an interesting idea, though. Yeah, I might look at it more after the session. So yeah, thanks for bringing it up.
Are we gonna solve this one like in the following sessions, or we just gonna do other ones?
I think in the next session, like we'll first solve a couple, and then if we finish them all, then we'll get to then we'll work on this one.
Yeah, I'll try to work this one on my own too, and if I can solve it, I will just post it on Discord.
Yeah, if you can solve it on your own, just post it on Discord. Yeah, you don't have to worry about like. Yeah, if you solve it on your own, just share it with everyone. I think it would be fun. So yeah, thanks again, everyone, for participating. Yeah, thanks for helping support the channel. So I think next time I'm going to keep doing more Saudi Arabia team selection tests for all their different contests. So thanks to Khan for sharing this contest. So if you would like to join future sessions, you can email me at mgreenb801@gmail.com. It's going to be in the description of my video, and we meet at 8 a.m. US Central Time every Sunday. Thanks for watching and have a good day.